examples where the iPS cells are giving us insight into these two different disease conditions. Now, what I want to talk about is a couple of stories where we've started to learn some very interesting fundamental principles of reprogramming. And the first is the relationship between telomerase and telomerase function, known to be critical for cellular immortalization, and the reprogramming process itself. What has been known is that the cocktail of 4 transcription factors activate an entire network of genes that are required for pluripotency, including the reactivation of the catalytic subunit of telomerase. Here are just reprogrammed state. You can also see this above by telomere length analysis that the rather shortened telomeres of the fibroblasts are regrown with reprogramming. Now, this mimics what's been observed in somatic cell nuclear transfer, where one can actually reactivate the telomerase machinery through reprogramming and lead to the regrowth of telomeres. Now, with iPS cells, what we've been able to do is literally subclone the fibroblast and demonstrate in 3 independent subclones that the telomeres will regrow. So the reprogramming is not simply identifying those rare cells in the population, but have retained long telomeres, and so therefore are more susceptible to reprogramming. The reprogramming process itself reactivates telomerase. So Sunit Agarwal in my group has been interested in asking, using a disease-specific model, whether or not the reactivation of telomerase is an essential feature of reprogramming. And for that, he turned to patients with a disease called dyskeratosis congenita, which has been linked to defects in the telomerase enzymatic machinery. And indeed, one can find mutations that influence the catalytic subunit of TERT, the RNA component TERT, or various RNA binding proteins like disperin, which act to bind and stabilize the core TERT. And there's some fascinating manifestations of this condition, but we are particularly interested as hematologists because we're seeing mutations in the pediatric hematology clinic of bone marrow failure. So Sunit obtained fibroblasts from individuals and then asked whether or not you can indeed affect reprogramming in the absence of bona fide telomerase activity. And here were just 2 of his early passage iPS clones, which were derived but with low efficiency. And in this case, there was a progressive loss of telomere length from the starting fibroblast to the early iPS. Now, this suggested to us that you could dissociate the phenomenology of telomere length extension from reprogramming, and the reprogramming was, in a sense, independent. But as we carried these further to later passage, what we found was a restoration of telomere length, which was really quite startling to us. And so Sunit attempted to then ask questions about the mechanism of this telomere regrowth. We thought because it was a slow and steady increase rather than a saltatory dramatic increase, which might have been seen in the so-called alt strategies, what we focused on was the expression of the RNA component itself. Now, the standard view of telomerase regulation is that the RNA component is a tonically and constitutively expressed component, and that it's the catalytic subunit which is regulated. But here in the wild-type fibroblasts, we have RT-PCR measuring the amount of the TERT RNA component. And in 2 different allelic defects of the disperin RNA binding protein, that's dramatically destabilized. But what we see in the the resulting iPS cell is that the expression of the RNA component is restored. Now, this suggested a upregulation of the RNA component. And so we asked what happens in wild-type reprogramming, and indeed we saw an expression above the wild-type levels. And that was seen not only in iPS cells, but in human embryonic stem cells. So it suggested that the upregulation, or the higher steady-state expression of the RNA component, was a property of the pluripotent cells. So looking at what the underlying basis of that was, Sunit and John Lowe and my group performed chromatin immunoprecipitation using antibodies against OCT4 and NANOG, here a direct reprogramming factor, and NANOG being a factor that's activated as part of the pluripotency machinery. And what you can see in two different iPS isolates is indeed direct binding of these two elements of the pluripotency machinery into the locus of the RNA component itself. Now, interestingly, we still don't completely understand how this leads to the steady-state increase in RNA expression, because this is a very long-lived RNA. We've not been able to demonstrate by runoff analysis that there is transcriptional upregulation. But what we've observed is we've looked at the other components that we've been assessing, the disparent RNA itself, and indeed what we see in now three different fibroblasts that carry the disparent defect is that in all cases with return to a pluripotent state, the disparent RNA is also upregulated. And by chromatin immunoprecipitation, we can show that the OCT4 and NANOG pluripotency factors bind in the locus of disparent. So we now have examples where three of the components of the telomerase machinery, the catalytic subunit, the RNA component, and the RNA binding protein disparent, are all upregulated. And we believe this is a novel principle of telomerase regulation in this rapidly growing pluripotent stem cell. So here is an example how a foray into disease biology has allowed us to explore and understand and make a new insight into the regulation of telomere biology. And I think these new approaches using stem cells are going to lead to even more unanticipated insights. So another disease that we've attempted to reprogram are mitochondrial diseases. Now, these are particularly amenable to an iPS approach as opposed to a nuclear transfer approach, because in nuclear transfer, you substitute the donor mitochondria for the recipient oocyte. So this started with a patient that Sunit and I saw in the hematology clinic, a young girl who had had transfusion-dependent anemia of unclear etiology since birth, but at age 3 started presenting to our emergency room with a complex of metabolic disorders, including diabetes, pancreatic insufficiency, and lactic acidosis. The lactic acidosis suggesting to us that there might be a metabolic and mitochondrial defect. And so from the bone marrow biopsy that we performed, we also used PCR to look at the mitochondrial genome and indeed detected a large deletion. And the fact that we saw this complex of clinical symptoms as well as a mitochondrial defect nailed the diagnosis as this rare Pearson's narrow pancreas syndrome. Now, this is part of a spectrum of mitochondrial disease, which is really quite fascinating because these have a very pleiotropic kind of presentation depending on the segregation of the deleted mitochondrial genome. So indeed, you obviously have a combination called heteroplasmy within this particular cell with deleted